let's talk about accuracy and precision. So accuracy and precision are very important concepts to take into effect when we're talking about data collection and measuring in science. And especially when using equipment, it's important to take that into effect. We're going to talk more about accuracy and precision related specifically to equipment in a later online note. But right now it's important to remember that accuracy and precision are not unrelated topics. The best results come from being both accurate and precise. The accuracy of a measurement is based on how close a measurement is to a known value. So when we're thinking about accuracy, we're thinking about comparing a value that we get to a known value. So for example, in an experiment designed to determine the density of water, a student calculates the density of water at 0.95 grams per milliliter when the actual density of water is 1.0 grams per milliliter. So looking there, if he was to determine the accuracy of that experiment, he would look to see how close his value of 0.95 is to the known value of 1.0 grams per milliliter. Precision, the precision of a measurement, comes from how close a series of measurements are to each other. So in precision, we're not comparing a value to a known value, we're comparing measured values to each other. So when determining the density of water, the student repeated the experiment 3 times, and for each trial, the following results were determined. He got for the density of water 0.96 grams per milliliter, 0.94 grams per milliliter, and 0.95 grams per milliliter. So in determining his precision, he's going to look at how closely related those 3 values are. Accuracy and precision, like I said, are not independent things. The best results do come from results being both accurate and precise. But let's take a graph and look at the best depiction of accuracy and precision, which is this nice little target with the bullseye. So over here, there's my mouse. Over here, we have a target that is neither accurate nor precise. So if you look at these darts over here, it's a target, so this center red dot or the bullseye is where they're aiming for. If they aimed here, that's where you're most accurate. As you can see, these darts are all on the outside, so this is not an accurate firing of darts. And they're all spaced out. They're not grouped together, and so it is also not very precise. He was not accurate and not precise. So this is an example of low accuracy and low precision. Over here, again, the same target. We've got our bullseye that we're aiming for. The darts over here, again, not hitting the target, not hitting the bullseye. So they are not accurate. They have low accuracy. However, these darts this time are not grouped all over the board, but are actually grouped together in this nice, tight little grouping. And so he had high precision here. So this is a nice example of low accuracy, but high precision. Over here, our darts are getting closer to our bullseye. They're getting closer to the most accurate place. And so here, these darts actually show pretty high accuracy. They're getting much closer to the bullseye than they were when they were in this green section. However, the darts are still not very tightly grouped in this one, and so this is an example of high accuracy with low precision due to this large, non-tightly grouped pack here. Over here in our final dart board, we can see the best example. And here are 3 darts hit right set dead on in the center for high accuracy, and those 3 darts are very tightly grouped for also high precision. So this is an example of high accuracy where we're getting that known value, and we're also very precise. We got repeatable results. So let's talk about an example here. I have a student, and they're measuring the density of copper. She calculates 3 values, 6.37 grams per milliliter, 6.34 grams per milliliter, and 6.30 grams per milliliter. When she looks it up online, she can find that copper's known density is 8.96 grams per milliliter. I want you to take a minute and pause the video right now and analyze her data to determine if her results were accurate, precise, both, or neither. So please take a minute now to pause the video and think about her data. Alrighty, so I hope you've thought about the data and you thought about determining whether it's precise, accurate, both, or neither. The answer is that the student's results were precise but not accurate. And this is because her results were very close to each other, but they were far away. So they were very close to each other, giving her precise, repeatable results. However, they were further away from that known or accepted density, so they couldn't be considered accurate. So she got very repeatable results for that density of copper. However, that density that she calculated, not as close as to the actual density, so it was not accurate. She was precise, but not accurate. One of the best ways to determine precision and accuracy is to take on a set of measurements is to take the percent error. And percent error is calculated using the formula actual value minus theoretical value divided by theoretical multiplied by 100%, because we want the percent error or the percentage error. And so in order to get it into a percentage, you must multiply by 100. In this equation, the actual value is the experimentally determined value. This is the value that you would get from your experiment. This is your results, essentially. And the theoretical value is the accepted or known value, the constant. So in that last example where we were talking about the density of copper, the actual value was 6.30 grams per milliliter. The accepted or theoretical value is that 8.93 or 96 grams per milliliter, that known value. So again, the actual value is what you determine, what you're getting, the actual value that you get, and the theoretical value is the accepted or known value that the literature states. So let's talk about some examples with percent error. Water's known boiling point is 100 degrees Celsius. I have a student, and they're asked to determine its value experimentally. The student's thermometer reads 98.9 degrees Celsius when the water is boiling. What is the student's percent error? So I'd like you to pause the video now and calculate the percent error. Alrighty, thank you for pausing. So let's figure out how we would calculate that percent error. Again, the percent error is the actual minus theoretical divided by theoretical times 100. So in this case, the actual value was 98.9 degrees Celsius. That is the value that the student recorded from his thermometer. The theoretical value is 100 degrees Celsius, or 100.0 degrees Celsius, and that is that known value. And so his percent error would be 98.9 degrees Celsius minus 100 degrees Celsius divided by 100.0 degrees Celsius multiplied by 100 to get it into that percentage. And the percent error is therefore negative 1.1%, or just written as 1.1%. Oftentimes, percent errors should be written without signage, so no negative or positive, because it's technically an absolute value. But sometimes it's good to note the negative so that you can understand whether the percent error is whether they were under the known value or over the known value. I will accept either. Let's look at a second example. So there's a cell that the student is studying, and it has a known diameter of 2.2 times 10 to the minus 2 millimeters. A student measures the cell and calculates a diameter of 1.22 millimeters. What is the student's percent error? Please pause the video and calculate our student's percent error for her cell diameter. So when determining that cell diameter error, again, you're going to take actual minus theoretical divided by theoretical times 100. So here the actual value is 1.22 millimeters. That's the cell diameter that the student measured, subtracted by the known diameter of 2.2 times 10 to the minus 2 millimeters, divided by the known value times 100. The percent error for this student, let's check your results, is 5,400% error. Okay. I chose these two examples because I wanted to talk to you about how important percent error is. In that first example where we're talking about water's boiling point, the difference between 100 and 98.9 degrees Celsius is only 1.1 degrees Celsius. The difference in the cell experiment, where between 1.22 millimeters and 2.2 times 10 to the minus 2 millimeters, is 1.198. Okay? So we're looking at two differences, two very small differences, 1.1 and 1.198, and yet they yield two completely different percent error values. And that's what's important about percent error. It allows us to look at the values and see, based on the overall experiment how close two things are, because we might think that 1.198 millimeters, that's not a lot of a difference, but when the known value is something that's so small and she's getting a larger difference like that, the percent error is huge. And this is why we use percent error. It's a great way to tell us whether or not what we think might be accurate or precise is in fact not accurate or precise. Alrighty, if you haven't already viewed the significant figures online presentation, please take the time now to go over and review that. Otherwise, I will see you tomorrow.